The story of gold almost never begins with gold. It begins with stone that looks ordinary, broken ground most people walk past without a second glance, and a landscape that keeps its secrets quiet. Every major gold discovery in history shared one thing in common. Someone understood what the rocks were trying to say before the gold ever revealed itself. And among all the rocks that have carried gold across geological time, none have played a more important role than quartz. Quartz veins are not random. They are the fingerprints of ancient pressure, heat, and movement deep within the earth. When you learn how to read them, you stop guessing and start seeing patterns that have guided prospectors for centuries. This is not about luck. This is about understanding how gold chooses where to hide. Quartz itself is everywhere, which is why most people misunderstand it. White quartz, milky quartz, clear quartz. These appear in countless environments that contain no gold at all. The mistake beginners make is assuming quartz equals gold. In reality, gold only bonds with quartz under very specific conditions, and those conditions leave behind clues that are visible long before a hammer ever touches stone. Gold-bearing quartz veins form when superheated fluids move through fractures in the Earth's crust. These fluids carry dissolved minerals, including gold, under intense pressure. When the pressure drops, often because of fault movement or cooling, the minerals precipitate out of solution. Quartz crystallizes first, forming veins. Gold, heavier and slower to settle, follows behind, lodging itself in cracks, pockets, and microscopic voids within the quartz structure. This process doesn't happen once. It happens over thousands, sometimes millions of years. Each pulse leaves behind another layer, another opportunity for gold to concentrate. That's why rich quartz veins often show complex textures, banding, layering, shattered patterns that look chaotic but are anything but random. The first thing to understand when identifying gold-rich quartz is location. Gold does not distribute evenly across landscapes. It favors ancient geological environments that have already proven they can host mineralization. Greenstone belts, old mountain ranges, fault zones, and shear zones are among the most productive regions on Earth for gold-bearing quartz. These areas experienced repeated tectonic activity, which created the fractures necessary for quartz veins to form and for gold to accumulate. When walking terrain with potential, quartz veins rarely appear isolated. They tend to occur in systems. One vein often leads to another, sometimes parallel, sometimes branching like roots. A single exposed vein on the surface may be the visible tip of a much larger structure hidden underground. This is why experienced prospectors don't focus on one rock. They read the entire hillside. Color is the next signal, but not in the way most expect. Pure quartz is white or translucent, but gold-bearing quartz is rarely clean. Iron staining is one of the strongest indicators. Rusty reds, browns, and yellows suggest the presence of oxidized sulfides, which are often associated with gold. When you see quartz with iron oxide streaks, especially near faults or fractures, you're looking at a system that once moved mineral-rich fluids. Texture matters more than beauty. Gold prefers broken quartz. Veins that look shattered, brecciated, or fractured are far more promising than smooth, glassy quartz. Those breaks created space for gold to settle. Sometimes a quartz looks crushed, as if it was forced apart and re-cemented. These are signs of repeated movement, and repeated movement is what concentrates gold. Another critical indicator is the host rock. Quartz veins cutting through dark, iron-rich rocks like basalt, schist, or greenstone are historically among the most productive. These rocks react chemically with mineral fluids, encouraging gold to drop out of solution. When quartz veins run through soft, altered rock that looks bleached or clay-like, that alteration is a chemical footprint left behind by hot fluids, and gold often traveled with them. Sound is something few people talk about, but experienced prospectors notice it instantly. When struck with a hammer, barren quartz rings sharply. Gold-bearing quartz tends to sound duller, heavier. That sound comes from density changes caused by sulfides and metals embedded within the stone. It's subtle, but once you hear it, you never forget it. Surface clues often lead downhill. Quartz veins erode over time, releasing fragments into surrounding soil. This creates float, loose pieces of quartz scattered downslope from the source. Following float uphill is one of the oldest prospecting techniques in history. As the pieces become larger and more angular, you're moving closer to the vein itself. When the float suddenly stops, the source is often just above. Vegetation can also betray hidden veins. In mineralized ground, plants may appear stunted or discolored due to metal content in the soil. In dry environments, quartz veins sometimes support different vegetation patterns because of how they affect moisture retention. These signs don't confirm gold, but they point toward geological disruption. And disruption is where gold hides. Not all gold-bearing quartz shows visible gold. In fact, most doesn't. The gold may exist as microscopic particles locked inside the quartz matrix. This is why visual inspection alone is unreliable. The richest quartz veins in history often looked unimpressive until crushed and processed. What matters is context, not sparkle. Vein orientation tells a story. Vertical or steeply dipping veins often indicate deep-rooted systems that may continue far below the surface. Flat-lying veins can be rich but limited in extent. When multiple veins intersect, those junctions are prime locations for gold concentration. Pressure drops and fluid turbulence at intersections allow gold to settle more easily. Faults are especially important. Quartz veins that run alongside faults or shear zones benefit from repeated fluid movement. Each seismic event reopens pathways, allowing more mineralization. That's why many of the world's largest gold mines sit directly on ancient fault lines, even if those faults are barely visible today. One of the most overlooked indicators is quartz that contains dark mineral streaks or tiny black crystals. These can be sulfides like pyrite or arsenopyrite, minerals commonly associated with gold. While not all sulfides mean gold, gold rarely appears without them somewhere in the system. Learning to identify gold-rich quartz is not about memorizing rules. It's about training your eye to recognize environments where gold can exist. Every clue adds weight. No single sign confirms anything, but when multiple indicators overlap, iron staining, fractured quartz, favorable host rock, fault proximity, the probability increases dramatically. This is the point where most people stop looking and start smashing rocks blindly. That's a mistake, because before a single stone is broken, before any gold is released, there is a crucial moment where understanding turns into intention, where you decide which quartz deserves the effort and which will waste your time. And that decision determines whether the next step reveals nothing or changes everything. And that's where this guide goes next. Once the right quartz has been chosen, the work changes character. Up to this point, everything has been about observation, patience, and restraint. What follows is physical, methodical, and unforgiving of shortcuts. Gold does not release itself easily, even when it has already been found. The first transformation is not about breaking quartz completely. It is about weakening it intelligently. Quartz is hard, but it is brittle. When force is applied correctly, it fractures along natural lines created millions of years ago. When force is applied carelessly, it absorbs energy and wastes effort. This is why experienced hands never rush the first impact. They read the stone one last time, looking for hairline cracks, stress points, and internal planes that hint at where the quartz wants to separate. When the quartz finally breaks, it does not explode. It opens. The sound changes. The resistance changes. Fresh surfaces are exposed that have never seen light. This is where gold begins to reveal whether it exists at all. Sometimes it shows itself immediately as dull, yellow streaks embedded in white crystal. More often, it stays hidden, still locked inside smaller fragments that require further reduction. At this stage, size matters more than force. The goal is not powder. Powder traps gold. The goal is controlled reduction, breaking quartz down until the gold can separate naturally under gravity. As pieces become smaller, density starts to matter. Quartz becomes lighter relative to gold. That difference is the entire foundation of natural gold extraction. Water enters the process not as a solvent, but as a separator. Flowing water does not dissolve gold, it sorts it. When crushed quartz is introduced into moving water, lighter material is carried away first. Heavier material resists movement. Gold resists the most. This behavior has not changed since the first rivers formed on Earth. When material moves through water, shape becomes important. Flat particles drift. Rounded particles roll. Dense particles sink quickly and stay put. Gold tends to flatten as it breaks free, which makes it behave differently than quartz fragments. This difference is subtle, but it is consistent. Nature has already done the physics. The process simply allows it to reveal the result. As lighter material is washed away, concentrates remain. These concentrates are not gold yet. They are a mixture of heavy minerals that share similar density. Black sands, iron minerals, and other dense fragments accumulate together. This is where patience returns. Rushing here destroys recovery. Everything valuable is now close together, and separating it requires calm, controlled movement. Gold does not cling to quartz once fully liberated. It prefers the lowest point, the quietest place, the moment where motion stops. When movement slows, gold settles first. Everything else arrives later. This timing difference is critical. Watching how material settles tells more than color ever will. Mechanical separation continues gradually. Each pass removes more unwanted material, leaving behind a smaller, heavier concentrate. The volume decreases. The weight feels wrong for its size. This is when gold begins to assert itself physically. Even without seeing it clearly, you can feel it. Eventually, gold appears unmistakably, not shiny at first, often dull, rough, and mixed with residue. This surprises people who expect instant brilliance. Natural gold rarely looks like jewelry. It looks like something unfinished because it is. The final separation before melting is about isolation, not extraction. At this point, gold exists as solid metal again, no longer trapped, no longer hidden. It must be cleaned mechanically, not chemically. Water, gentle abrasion, and repeated settling remove remaining debris. What remains is metallic truth. Only after gold exists as itself does heat return to the process. Heat is not used to find gold. It is used to unify it. Individual flakes, grains, and fragments are brought together so they can become one mass. This is not refinement. This is consolidation. As gold heats, it does not burn, evaporate, or degrade. It softens, then flows, pulling itself together naturally. Impurities that survived mechanical separation resist joining and are pushed aside. Gold wants to be whole. Heat simply allows it to act on that preference. When the metal gathers, it is still not pure in the commercial sense, but it is gold in the geological sense. Elemental, real, and free. This is the moment where nature's work ends and human intention begins. And this is where the process transitions again, because turning released gold into something permanent requires a different kind of discipline altogether. One that has nothing to do with rocks, water, or force, and that comes next.